L. I should figure out how to do this. Settings. Gonna have to do windowed, maybe a lower resolution. I'm working with one monitor right now. I should have thought about this. Off to a good start. Okay. Sources. Game capture. Alright, looks fine. How do I transition to... There we go. Hello. We're doing a very janky one monitor, no stream deck stream. Just me and my mouse and my keyboard. Let's learn quantum mechanics. Is there a way to like reset my progress? Because I don't remember anything about what I've done. I guess not. Okay. What is going on? Okay. So, quantum arena. Is there a way to reset my progress at all? I really don't remember anything. Okay. I guess I'll just hop into the beginner stages and go from there, huh? Unveiling the forge, time... Okay, let's do this one. Unleash the forge and begin your odyssey toward mastering the nature of reality. In the hands of an adequately trained smith, this device can craft quantum algorithms of immeasurable power. Seeker, welcome to the forge. This is your tool to build and test quantum ideas. You've been chosen to shape the logic of our universe. Your path starts here. Press key R or click... Oh, that little button to proceed. Wait, what? Okay. Camera movement. Hold right click to move camera and large puzzles. WASD, recenter F, zoom with the mouse wheel. About the moving sphere, it simulates the quantum state vector of a single qubit evolving over time. Okay, so there's a lot of background information, or a lot of just words being thrown out here. So, gosh, where do I start? So the world of quantum mechanics is a world of probabilities. And, oh, hi, Maddie. Thank you for the follow. How are you doing? I'm doing a pretty janky stream. I hope my bitrate is showing red. I hope that's not a problem. We'll see. So where was I? Okay, so we're at the first stage of Quantum Odyssey. This is a game where we solve puzzles and learn. What keeps disconnecting? There's nothing to be disconnected. Okay. Where we solve puzzles and learn about quantum mechanics and quantum computing. Right. What do you mean USB? What USB device? What is it? This thing? I'll unplug it. Jeez. Anyway, so the way quantum computing works, as far as I understand, is that instead of bits, we use qubits, which I think for most implementations of quantum computers, they use electrons because actually, let me bring up Microsoft Paint. Is that the right one? Okay. So instead of bits, God, I can't even find my drawing tablet. Instead of bits, we have qubits. And for bits, we have zeros and ones that more or less, either mechanically or magnetically or by other means, flip between one and the other. And once we have a lot of bits, we can store information and do calculations with them. Qubits, on the other hand, are made up of quantum particles, usually electrons, I think, from my understanding. I'm not a quantum computing expert, so bear with me. And the reason electrons are useful is that if you look at an electron, it has a 50-50 chance of spinning in one direction or the other direction. And because of that 50-50 chance, we can call one of the directions the 0 and the other direction the 1. What I'm not entirely sure about how this all works is how do we manipulate the electron between 0 and 1. That you might have to ask an actual quantum computing expert, but as far as basic quantum mechanics goes, that is how it works. There's a 50-50 chance of an electron to be spinning in one direction or the other direction. So one of the directions is the 0 and the other is the 1. And that's how a qubit is formed. Let me go back to the game, if it will let me. Okay. So in this case, we're basically looking at one qubit. So it's one electron. And this is a really bizarre way to simulate this. So these two rails are basically the two states of an electron. Is it spinning clockwise or counterclockwise, basically? And if we play this simulation, so to speak, we're basically... How do I put this? So the way this works, I think, is that the circle or sphere being in this 0 rail means that the electron is spinning clockwise. And in order to solve this particular puzzle, we need to change its spin direction into the other direction so that it reaches its goal here. So that where the sphere is at the end is where this guy wants to go. It wants to meet its friend, basically. So yeah, if we pause, I guess that's what it's called, a sigil in the game's context. So right now it's saying that the electron is in the 0 state, or spinning clockwise in this case. And magnitude and the number above that sphere is, I guess what the game is calling its magnitude. And that magnitude is basically telling us the probability of the electron being in that particular state. So its probability is 1, which means it has 100% probability of spinning clockwise, unless we do something about it. So, information in our universe is conserved. It cannot be created or destroyed. The total amount always stays the same. It only changes form. Tools like our forge shape these transformations. The following sigil, a pure state vector, represents the cycle of change. Goal is to collide with a static sigil by etching its magnitude. Okay. So we want to change the electron state from turning clockwise to turning counterclockwise, in a sense. This doesn't have to be clockwise and counterclockwise. It can be the other way around. I don't know how the experts define it. Or I don't remember, I suppose. So it has to be... So we have to switch it from being at 100% probability of being 0 to 100% probability of being 1. So how do we do that? We have these gates, I suppose. I wonder if this explains how it actually works. I guess not. Okay. So this gate, so to speak, is going to switch 0s to 1 and 1s to 0s. Okay, there's a replay. Okay. So that's got to be some sort of operator that changes the state of the electron. I don't know how it would physically be implemented. This is just the math being shown here, I guess. But we're switching from 100% 0 to 100% 1. So, yeah, I've already done some of the stages, but I wanted to go through them again because I hardly remember anything. So that's basically just a bit flip. We switched a bit from 0 to 1. Let's see. Mechanics of the fracture. Time capsule. Poly XK. Jeez, okay, I'm gonna have to. Okay, let's just do the second one. Your cosmic keys. Delve deeper into the workings of your forge. Find out how state grabbers and space switches will become useful in designing quantum algorithms. Discover your knowledge vault. These fundamentals will get you all set to begin your training on what quantum gates can do. Oh, jeez. What the heck? Okay. Fill the circuit with quantum gates. They shift the state, vector, size, and direction. Like words in a sentence, gates and sequence form quantum algorithms. You'll learn to build quantum algorithms for any problem you can imagine. So this is just flipping a bit over and over again. Okay, let's get rid of all of these. Fixed gates are set up by the stages for training cannot be removed. Okay. Oh, that's it? With this visual method, mastering our universe's true logic is like our Rubik's Cube. Most give up, lost to trial and error. Good solvers average 7 seconds. Expert 3.13. Best see the hidden patterns that guide every move. But unlike the Rubik's Cube, the Forge's rules weren't invented. They were discovered to reveal how our universe truly works by exposing once hidden patterns of linear algebra. What you discover here matters. Most of the seekers on the leaderboard don't rely on math or chance. I hope it'll show you math was never scary, just poorly taught. By default, the Forge displays the full quantum Hilbert space. I'm just going all there. Okay. All possible quantum. Okay, so it's basically... The Hilbert space is basically... How do I even... It's a representation of all possible things. In a controlled environment, I suppose, in this case. So all possible things given certain conditions. So right now, we're just looking at one electron, and all of its possible states would be spinning in one direction or spinning in the other direction, which is why there are 2 rails. So all paths to gates create... Okay. The state view shows only the path sigil state. Oh, really? Huh. Switch views by clicking the pins under bit string sequences. Which pins? Oh. Oh, that's cool. Okay. There's a way to only see the path the quote-unquote sigil takes. Or the changes in the actual changes in the state of the electron, basically. Avoid using the state view until you understand the Hilbert space for each gate. Often the circuit becomes long and you'll find that your interests are focused solely on altering the bottom part. You can modify the spawning position of the sigil by using the advanced circuit tool. Click on any of the state grabbers to test this. Whoa, okay. So like copy tensor. What does that give me? Oh. Okay, what does copy state give me? 001 0110. Oh, okay. So it's the tensor is basically just the pretty much just the matrix. Okay, so copy tensor and like just the parallel ones gives me like the identity matrix, and the bit flip ones gives me the inverse matrix. Okay. What about this? Oh, it skips all the other parts. Okay, cool. Hover over red words for detailed definitions like xgate. So flips the bit. Most red words are real quantum computing terms. They'll appear across puzzles to draw you deeper into the concepts. Explore when curiosity calls. Take your time and let your mind weave new connections through repeated encounters in different settings. The sages don't expect you to read anything at once. Quantum intuition. Time spent is shown, but never a factor in calculating rewards. Rushing steals understanding. To finish this tutorial, drag one xgate into the circuit configuration. Okay, yeah, I mean, because it just keeps landing there, so just one bit flip is gonna do the trick. That's cool. I wonder if they added like the copy tensor stuff like after I played it last time. I don't remember that being a thing. Okay, forge inner workings. So we're still doing one bit. There are now two sigils on the screen. Sigils are the coefficients of a pure quantum state vector. Complex states like this superposition use multiple sigils since the system is in multiple states at once. When there is more than one sigil, you will always see them falling together. Their combined sum describes the full quantum state vector. How do I not see that? The whole overlay. Is it that? Okay. Sigils are visual representations of the complex numbers that make up the quantum state vector. They have three properties you will work with. Direction, given by their bit location and shown by the kets when you hover over them. Size. The magnitude of the complex number inside. Direction. Okay. Color based on the signs of the real and imaginary parts. Press Q. Oh shit, okay. They're just throwing us in there. Okay. Which turns all possible quantum and math code into pure visuals. With state vector turned info turned on, you'll see how complex numbers add and multiply. Core to quantum mechanics. You'll never see numbers above 1. Hate math. Turn it off. Your visual intuition is enough. Roll the mouse wheel over the bottom part of this. Oh, okay. So that's the solution, but I want to go a little deeper into what's going on here. So, God, I'm bad at explaining quantum mechanics. So I guess we're going back to Microsoft Paint. Okay. Uh, I am alive. Okay. Ah, yes. Quantum states, yes. So. So, I said earlier that an electron. Why is that so thin? What the fuck? That's better. That an electron has two different states. Let me have some fun with the colors. Okay. You know what? I'm gonna fill it blue. That's not full at all. There we go. Okay. Electron can have one of two states. That is determined by the direction of its spin. It can spin in one direction, it can spin in the other direction. And, well, I mean, if I'm being completely honest, this is not literally the electron spinning in one or the other direction, because they're basically just dots, but they behave as if that is what's happening. So it's a good shorthand to think of it like this. Anyway. In short, to make things simple, we call this spin up and the other one spin down. And let's say spin down is 0 and spin up is 1. An electron that can either be spinning up or spinning down is going to have I guess ideally it would be just a 50% chance of spin up or a 50% chance of spin down. But probabilities of things happening can change. Like if we take a coin flip, for example. If we have a coin that can be either heads or tails, for an ideal perfect coin, it would be a 50% chance of being heads and a 50% chance of being tails. But we can do things to the coin that changes those probabilities. Like, I don't know, like we could pretend to flip the coin and just keep it on heads, in which case it would be 100% heads and 0% tails. Or we could add a weight on one side to make it 70% chance of heads and 30% of tails. So we're going to see a combination of probabilities that add up to becoming 1. So probability of heads plus probability of tails is going to be 1. In a similar sense, the state of the electron is going to be a combination of states with their probabilities, or not exactly their probabilities, but an analog to their probabilities. So an electron with 100% spin up chance would just be this fun little bracket looking thing with a 1 inside. That we call these kets. In the context of bracket notation, because they're I don't know if they're going to be introduced here, but there's another way, or there's another kind of state, so to speak, that is represented with, let's just write an X for some random number. That's represented by like the left-hand side of the bracket. So we call those bras. And the right-hand ones we call kets. But let's stick to kets for now. So an electron with 100% probability of being spin up is just going to be the 1 ket. And 100% probability of spin down is going to be the 0 ket. An electron with a mix of those probabilities is going to be some number, let's call that C1, times the first, times the 1 ket, plus C0 times the 0 ket. State of electron. So that means it has a mix of probabilities of being spin up and being spin down. The reason I am not calling the C1 and C0 a probability necessarily is because it really is not. So let's, I'm just going to go with the formal-ish notation. So we use Greek letters in physics for some reason a lot of times. And for the electron, I'm just going to use a psi and a ket. So this means that the state of the electron is a combination of some probability of having spin up state, or spinning in, I guess, a counterclockwise direction, and another probability of having a spin down state, or in this case, spinning clockwise. To know what the probabilities of those two states are, we can multiply it by the bra of its state, which in this case means gosh, how do I even explain this? I guess I'll have to write out like what the bra would be. So the bra of the electron state is going to be, let's say, C1 star times the bra of 1 plus C0 star times the bra of 0. This is, I'm doing this purely from memory, so I may be wrong somewhere. Hopefully not. And the gist is that if we multiply this guy by this guy, we're going to have the full combination of the probability of 1 and the probability of 0, and it will add up to 1. In this case, the way we find each of these probabilities is we match the numbers in the bras and the kets and multiply the matching terms. So in this case, it's going to be C1 times C1 star times 1, 1 plus C0, C0 star times 0, 0. So that C1 times C1 star is the probability of the electron having a spin of 1 or spin up or being in the state of 1. And C0 times C0 star is going to be the probability of the bit being 0. Generally speaking. Unless there's some shenanigans. C1 and C1 star are a lot of times going to be the same number, which means oftentimes C1 times C1 star is just going to be C1 times C1, so C1 squared. Likewise for C0. But sometimes that's not the case, because for some reason in quantum mechanics, imaginary numbers are very useful in explaining how probabilities work, which is very bizarre. But it works. I'm a physicist, and I honestly don't really get why it works, but it does. So to explain how this imaginary number stuff works. Gosh, do I have to like zoom out? Okay. So let's pick a random C. So let's say we have an arbitrary C out of C1 and C0. It's going to be a combination of a real number and an imaginary number. Imaginary numbers are pretty much defined by having the quintessential imaginary number I which is the number that if you take the square root of gives you -1. If you remember math or how numbers work, usually when you take the square of a number, or any number, let's say x squared, it's usually going to be at least 0. It's going to be larger than or equal to 0. But for some reason, mathematicians found it useful to have a number that if you square gives you -1. And for some reason, using this number really works for well in figuring out real probabilities. Anyway, so let's say a is a real number. And b times I. So that's b is a real number and I is the imaginary number I. So b times I is imaginary. Not by people. By people are not imaginary. I mean, I guess there are imaginary by people, fictional ones, but by people in general are not imaginary. We can take the gosh, what is that called? I think it's called a complex conjugate. Okay. I'm skipping steps here. Okay, so a combination of a real and imaginary number is something that we call a complex number. Because, I mean, it is getting complex here. And because A and B can be any real number, technically, one could say that any real number can be a complex number because you can just set b to 0 and it gives you a real number. And an imaginary number is also a complex number because you can just set a to 0. But that's besides the point. We can also define C star as a similar looking number, except the imaginary part is going to be in the opposite sign. So it's going to be whatever the imaginary part was of the original number times -1. And if you multiply a complex number with its complex conjugate, we end up getting a squared plus b squared. I could do the algebra, I guess. I don't know what the preference would be for people. You might as well. Because it's going to be a plus bi times a minus bi. So what do we got? A squared plus or minus abi plus abi minus b squared I squared. The minus abi and plus abi cancel out. I squared is -1. So -1 times -1 is 1. So we end up with a squared plus b squared. C1 star is going to be the complex conjugate of C1. C0 star, the complex conjugate of C0. So essentially, the probability of the electron being in the one state is going to be C1 times its complex conjugate. The probability of being in the 0 state is going to be C0 times the C0 complex conjugate. which is basically like the magnitude squared. As we like to call it. So if C1 is just a regular old number like 0.5, for example, the probability is going to be really easy to find. It's just going to be 0.5 squared or 0.25 or 25%. So that means like there's a 25% chance of the electron being in state 1. From which you can extrapolate that its probability of being in state 2 is going to be 75%. But things do get a little messy when imaginary numbers get involved. Gosh, I'm doing a physics lecture. Anyway. So here we are. So let me try and figure out what these colors mean. Okay. So basically, the left rail represents the 0 ket of the electron, and the right rail represents the 1 ket of the electron. So when we start out, how do I restart? Okay. When we start out, we're told that the electron has a 100% chance of being in the 0 state. So the electron state right now is 1 times 0 plus 0 times 1, or 1 times ket 0 plus 0 times ket 1. So 100% chance of being in the 0 state. But then we're faced with whatever that thing is, and the electron states split up into 2. And for some reason, the numbers we're given are 0.71 and 0.71, which, as you can see, do not add up to 1. Those add up to 1.42. But there's a reason that's the case. God, this looks like the screen of an... So right now, the electron is in a state of 0.71 times 0 plus 0.71 times 1. Now, I said earlier that these numbers are supposed to represent the probability. But, as you can see, 0.71 plus 0.71 add up to 1.42. Now that doesn't make sense because there's no such thing as a 142 chance of something happening. The probabilities have to add up to 1. However, if you recall, so that's our C0 and that's our C1 in this case. When C0 and C1 are real numbers, numbers with no imaginary component, the probability is just going to be C0 squared or 0.71 squared. What does that give us? Oops. About 50, about 0.5. I think 0.71 was like an approximation. So, squaring 0.71 gives us 0.5. And likewise for probability 1, it's also going to give us 0.5, which means that in actuality, these numbers mean that there's a 50-50 chance of the electron being in the 0 state and in the 1 state. I am getting followed by bots on Blue Sky. or it's roughly the way you can think about probability in this case. And then what happens is that instead of 0.71, the right guy became I times 0.71. I guess the green one, I guess the green rail is the one that like multiplies things by I. And then it multiplies by I again, which makes it I squared, which makes it -1. So -1 times 0.71 gives you -0.71. And then it keeps going. It multiplies by I again. Until it's back into its original state. And then I think the red rail multiplies things by -1, if I remember correctly. Yeah. -1. So the question here is going to be, how do we change an electron state from 0.71 times 0 ket minus 0.71 times 1 ket? In this case, I think we can use this guy. Oh, come on. Where's the... Yeah. Start here. Okay. I think we can use this guy. I hope. To try to merge the probabilities here. There we go. Whew. Was that the third one? Okay. Oh, what did I do? No. Get out. How do I leave? How do I... Main menu? Maybe I should like do like Newtonian mechanics or something first. Anyway. Time capsule of humans in competition. What does this one do? computation is new to you. Oh, okay. So this is about like zeros and ones and stuff. Okay. That's for if you like don't know how bits work, I guess. I could try to explain computer logic, but I don't know if I have the brain space for that today. Mechanics of the fracture. Basic game mechanics using just one qubit without quantum theory. Oh, this is if you just want to play the game. Okay. Interesting. I guess that's like there was a part 2 that I guess part 2 might have been added as like an update. Huh. This is cool. Okay. The alphabet of our universe. What is this one? You don't need all that quantum theory. I guess I went 84%. These glyphs say it all. Trust your intuition. Spot the patterns and dive in. Start. Okay. You know, let's do the main track. Poly X gate. You're now ready to begin your quantum gates training and receive your first gate, the X gate or Poly X gate. It's a quantum gate that flips the state or qubit, changes the state from 0 to 1 and from 1 to 0, similar to the classical NOT gate. I mean, we're basically doing basic computer stuff anyway. Okay. So here it's just we're flipping a bit. And we're flipping a bit again. By manipulating probability through some mysterious means. I am not a quantum computing expert, unfortunately. Okay, so now we're looking at a combination of 2 bits or 2 electrons, so to speak. So now it gets a little bit, it starts to get a little more complicated. So because now we're looking at both of them being at 0, 0, first one being 0, second one 1, 1, 0, and 1, 1. And these are all different probable states. In this case, I think all we have to do is flip the second bit. Here we just flip the first bit. So we're doing very like deterministic bit flipping here. We're just switching from 100% to 100%. Now we're 3 bits. Okay, the middle one. What? I thought. Oh, all of. Wait. I misread. Just gotta flip the first one and then flip the second and third ones. jeez, okay. Where does it land? 1111. We want to land at 1001. So flip the second and third bits. I think we should be a-okay. Yeah, okay, so that's just explaining the mechanics of bit flipping, I think. Oof. Oh, my head. Let's do the master the bit flip part. Sure, why not? So now we're just flipping bits like there's no tomorrow. I mean, yeah, I know I've completed all the wait, oh, that's it? That's the only... I feel like I'm doing the same thing over and over again. Oh, there we go. Okay. Switch puzzle. This interface is confusing. Yay. Oh, wait, no, that's not. That's not. Oh, my God. What is going on? All right, let's try this again. Speed it up. Why does it keep sending me back to the first one? Stop sending me back to the first one. There we go. Is that the third one? Fourth one? Alright. Just flip the second one. And then the last one should be... Okay, so where does it land? 010. We want it to land on 111. Flip the first and third ones. And there we go. Easy enough. Alright. Let's try poly Z gates. This gate doesn't flip a bit like the X gate. It introduced the color red. So red in this case is negative. It means it becomes -1. Let's see, yeah, X. I guess they use X times 0 plus Y plus 1. Instead of like C0 and C1 that I did. Blah, blah, blah. Yeah. Okay. State info button next to the red state info button. What? Circuit tools. State info button. Oh, okay. Cool. Okay. Well, okay. So if we look at the state info button, we can see what's going on mathematically. So for each state, for each step, what's happening is that each step is multiplying a tensor, or basically a matrix, to the state, which is represented by a vector. So 1, 0, 0, 1 times vector 1, 0. If we go back to our trusty Microsoft Paint, so this guy basically represents 1 times the 0 state plus 0 times the 1 state. So these numbers go directly here into the vector. Multiplying these guys is going to be 1 times 1 plus 0 times 0. 1 times 1 plus 0 times 0. And 0 times 1 plus 1 times 0, which is going to be 1, 0. Which is why we call this guy the identity matrix. Because multiplying this guy to a vector is just going to result in the same vector. So it's basically the matrix equivalent of 1. Because if you multiply anything by 1, it becomes itself. Now, okay, maybe not here, but okay. 1, 0, 0, negative 1 is doing something different. Although 1, 0, 0, negative 1, if we multiply this by our same state, it's going to be 1 times 1 plus 0 times 0. And on the bottom, it's going to be 0 times 1 plus negative 1 times 0. So it is going to give us the same thing for this state specifically. But for a different state, like what if we had a 0% chance of being at state 0 because it was definitely at state 1? Now we get 1 times 0 plus 0 times 0, so that's just going to be 0. And on the bottom, we get 0 times 0 plus negative 1 times 1. So we get 0 and negative 1. So it flipped the sign of the 1 state. And I think you can tell what this one would do to a 1 and 0, which is basically just flip the top guy. Although it looks like in the game we don't have any option to do that. So right now, all we're doing is just letting this guy pass through and stay in the state it was in. What we want is for the 0 state to have a 0 probability, because we want it to be at 1, but we want it to be at -1. So what we can do is flip the bit and make it a -1 bit. So here we're just multiplying -1 and multiplying -1 again to turn it back into 1. Easy peasy. So here, what do we have going on? Okay. Blah, blah, blah. Yeah. So we want to flip the second bit, and I think we want to change its sign. Okay. So it starts at 000, and we want it to land at 111, but red. Let's flip the bit first. Yeah, I think we need to multiply by -1. Flip the bit and multiply by -1. Whew. Okay. Oh, I feel like I just gave a whole lecture. I mean, I guess I essentially did. But yeah, that's Quantum Odyssey. You can talk to me. I mean, you can listen to me yap about physics while solving puzzles. Oh gosh, I don't know how. I don't know how long I can sustain a Quantum Odyssey series. Oh geez, this is fun though. This is like, I'm like squeezing my brain for like all the quantum I learned in college. It's But yeah, I mean, like, if you kind of try to forget about like the existential horror that is why does any of this work? The math itself isn't too complicated if you like just hunker down and like do the algebra and stuff, I guess. But I think I think when I first learned quantum, what really got to me was like how just weird everything was. Like why does this math work? And like not getting what any of it really meant. I mean, I still struggle, to be honest. The trick for me personally was to not get too hung up on understanding it intuitively. Although things did get a little better when we started learning about like real world contexts of where this works, like an electron orbiting an atom, for example. I was like, oh, that's why this matters. But anyway, I think I can stop you. This is getting a little tiring to 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 do quantum mechanics. Let's see, who can I raid? Da, 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 Who haven't we raided? I mean, I guess we haven't raided anyone in a while. Uh, let's raid. Let's raid Dot. All right. As for Gammon.